Hey guys, sorry for the late lectures. I figured that you would want to hear me and not the music that my neighbors were blasting in the background last night. So, anywho, I wanted to go over a few problems that are going to stretch what you are comfortable with doing functional derivatives and calculus of variations. So these problems are going to be generalizations of what you see in the book, and it's going to make sure that you understand precisely what is going on with some of the steps that I would consider a little bit shady in the textbook. So here's what you've learned so far. You have learned if I have some functional, so basically something which depends on a function y, it can be defined like this. I can define it as an integral from x1 to x2 of some argument which depends on x, and then y, which is a function of x, and its first derivative. Cool, simple. And so we know that we get the Euler-Lagrange equations from taking a functional derivative. So basically, defining this in such a way where we can vary the path that, and what I mean by path is we vary which y we put in and look for the configurations of this integral, namely the solutions y that you could plug in, which make this integral a minimum value, right? And so the way that you end up doing that gives you a differential equation, negative d dx, partial L, partial y prime, plus partial L, partial y is equal to 0. So you get a differential equation out, you solve the differential equation, and that tells you all the different possible functions that you can plug in y, the solutions of the differential equation, that will make this S a minimum, a maximum, or some saddle point, right? Any extremum. So you've seen this already. Let's make this more complicated. There's no reason that we need to stop at one derivative. So I can do the following: more derivatives. Woo! S. I'm going to give you a different one. So let's say we have the same setup. We're going to define some functional, which just spits out, like it's nothing crazy. It spits out a real number. It gets defined in terms of an integral over x from x1 to x2. And the integrand, which, it's going to depend possibly on x. I'm also going to have it depend on y of x, y prime of x, y double prime of x, and to get really crazy, all the way up to the nth derivative of y with respect to x. So just for keeping notation clean, y to the k is just dky dxk. So the kth derivative of the function y. Okay, so in classical mechanics, the way it's set up is such that I'm going to define something called an action. And that action, if you take a functional derivative of it, so you try to figure out, what is the derivative of this quantity with respect to the function y. If you set that to 0, you get the Euler-Lagrange equations, which was on the previous slide. And those Euler-Lagrange equations essentially end up being equivalent to Newton's equations. Cool. Now, what happens here? So we know that if you have one derivative, we know what the answer is. It's the Euler-Lagrange equations. Do you get the Euler-Lagrange equations if you have more derivatives? And I want to also set this quantity equal to an extreme value, namely a minimum or a maximum? Well, I can tell you this, the answer is no, but we're going to go through the steps that actually get you there. So how do we figure it out? What we're going to do is the following. Vary y of x by alpha eta of x. So like in the book, alpha is a constant. It is independent of x. Eta is an arbitrary function. The condition I'm going to impose on eta is that eta x is equal to 0, eta prime of x is equal to 0, all the way to eta to the n minus 1. So the n minus 1th derivative is equal to 0. Now remember, we defined a functional s as being defined in terms of an integrand, which depends on y all the way up to its nth derivative. So that's why we have this n minus 1 here. You'll see why this becomes relevant just in one sec. So cool. When we vary s with respect to y, meaning that we take y and then we add alpha eta to it, what we're really doing is the following. We're saying s is a function of alpha now. It's equal to this integral. L depends on x, which doesn't have any variation, right? Because that's just x, it's not the function. Then we have y plus alpha eta, y prime plus alpha eta prime. Again, alpha is a constant, so there's no derivative with respect to it. Y double prime plus alpha eta double prime. Dot, 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 dot. Yn plus alpha eta n. Cool. So to figure out when s is actually at an extremum, if we were to set its derivative with respect to alpha equal to 0, what we're really saying is we want to figure out the configuration y, where if we were to perturb this by any arbitrary function, subject to the appropriate boundary conditions, where the strength of how much of that function we add to y is controlled by this arbitrary constant parameter alpha, all we're saying is that y would actually be the extreme value. And so we can ensure that by taking a derivative with respect to alpha and saying, hey, if this quantity is 0, we've actually found extreme values of this s quantity with respect to the y that is a solution of that differential equation. Cool. So ds d alpha has to be equal to 0 to find extreme values y to plug in that will extremize s. Very cool. And so like in the book, what that means is ds d alpha is going to be equal to partial L of x, y plus alpha eta, y prime plus alpha eta prime, yn plus alpha eta n, d alpha. And again, we're going to set that equal to 0. Cool. So how do we actually take this derivative? This was something that a couple of you guys came to me and were unclear of how to actually get the derivatives out just in the book for when you only have like y prime and we don't have these higher derivatives showing up. I'm going to show you how that works here. So I'm going to define y tilde k, which is a function of x and alpha, and this is going to be equal to yk plus alpha eta k. Both of these are functions of x only. So the alpha dependence only shows up in front of there. If you notice, this is what's showing up as the argument, or an argument whose derivatives we take in the integrand for s. Why is this important? Well, if I want to look at all the different partial derivatives, they go into like a chain rule here. So if I take partial L, partial alpha. This is going to be equal to the following quantity. The book says that in order to get this to be written in terms of derivatives with respect to y and derivatives with respect to y prime for the normal case, you need to use chain rule. What it doesn't tell you is you actually kind of need to use chain rule 3 times or twice. So here's what it looks like in our case. dl, dy, k, so that's for the kth derivative. We're adding up all the different dependencies on the different derivatives separately. That's what we want. The way that we get it is to say, well, this can be written as a derivative because we can invert the start equation over here with respect to y tilde k, and then we can take y tilde k and take a derivative with respect to alpha. So as you see, like the y tildes cancel if we cancel the numerator and denominator, same with the y's, and we get dl d alpha. Cool. So y is equal to y tilde minus alpha eta, which means that dy dy tilde and its k derivatives is equal to, oops, not 0, my mistake, it's equal to 1. That's a simple derivative to take. dy tilde d alpha is just equal to eta, and so that means that its kth derivative is equal to eta k, because that's what's showing up in front of alpha, and the y bit drops out. And so what that means is that ds d alpha is equal to this integral dx from x1 to x2 of the sum from k is equal to 0 to n, meaning we're tracking all the different derivatives, number of derivatives we can take of y, up to the nth one, because that's where we define that it stops. So this is kind of like what you have in the book. So we have eta, which is the arbitrary function, and we take k derivatives of it with respect to x, and then that multiplies the partial derivative of L with respect to the function yk, where yk is the kth derivative with respect to x of y. Cool. So what's important here is that we're treating, and this is a subtlety that doesn't quite get harped on enough in the book, this is a derivative with respect to a function, not with respect to a variable. But we're going to treat it as though the function is a variable for all intents and purposes. Here's where stuff gets freaky. Normally, when you are doing the derivation of the Euler-Lagrange equations, you just need to do integration by parts once. We want to express this derivative of s with respect to alpha in terms of eta times something, right? And so to do that, we need to get all the derivatives off of eta and put them onto the other stuff. And so we can go term by term. So if we look at the kth term in the sum, it's going to look like integral dx eta kx, partial L, partial y k, which is also a function of x. I'm going to make that very explicit for now. Cool. So if we integrate by parts, what we're going to get is the following. Eta with k minus 1 derivatives acting on it, partial L, partial yk. This is going to be evaluated from x1 to x2, and that's what this notation means, minus integral eta k minus 1 d dx of dl dy k of x dx. Cool. That vanishes. And the reason why is because we've imposed boundary conditions such that the kth derivative up through n minus 1 derivatives on eta vanishes at the boundary, and the boundary is x1 and x2, the bounds of integration. So basically, by doing integration by parts once, we get closer to the answer we want, which is we have eta with k minus 1 derivatives on it now instead of k derivatives. And that exchanges the derivative onto partial L, partial yk. Well, let's just do it again to see what happens. So let's repeat. Cool. So this is the expression that we ended up with. There's a minus sign there. So that minus sign is going to be important. Let's take another derivative off of eta. So we're going to do the integration by parts. We're going to just move a derivative over. So we're going to get eta k minus 2 d dx, because that's what shows up in the integrand of yk, x1 to x2, plus integral dx eta k minus 2 d squared dx squared partial L partial y k. Cool. So as you see, what's happening is as we keep doing this integration by parts, we keep losing derivatives on eta. As we keep doing it, we keep flipping the sign in front of the term that's left over. So as we go down the rabbit hole, we find that the kth term evaluates to up to the boundary terms disappearing, -1 to the k, because again, we alternate in sign every time we exchange a derivative. Cool. So that gets eta on its own. And what that means is that ds d alpha ends up just being a sum from having no derivatives to n derivatives that will be acting there'll be eta x, which depends on x only and no k, d x k k l dy k. Cool. And so again, now we're back to just what we have in the Euler-Lagrange equations, the same argument. Eta is in front of every term here, right? Because eta is in front of every term, what that means is that for this expression to be set equal to 0, and again, we are only setting it equal to 0 because we want to find the y's which extremize s, i.e. setting it equal to an extreme value, minimum, maximum, or saddle point. For this to be true, eta doesn't factor in because it's arbitrary. So eta shouldn't actually affect the answer. The other stuff in the integrand has to be equal to 0. And therefore, we get a modification of the Euler-Lagrange equation. So we get modified Euler-Lagrange equations. What we get is sum k is equal to 0 to n, -1 to the k, d dxk, dl, dy k should be equal to 0. This is a differential equation. You can see that because there's going to be a bunch of derivatives with respect to x on both y and then other ones that are acting on, just L and its partial derivatives. It will be a higher order differential equation than what you were dealing with before. So if n is equal to 1, that is what you were dealing with in the rest of the textbook. There's only going to be 2 terms here, namely the term where there's one derivative, partial derivative, and the other one where there are none. So we recover the normal Euler-Lagrange equations. So again, the purpose of this is just to challenge you and to show that there is a way to really push this to an extreme and see what, like a generalization in which you say, well, what if there could be more derivatives of y that show up in the expressions that we're dealing with, just to show what that actually does, and the fact that you can't rely on just memorizing the Euler-Lagrange equations, that would be no good. Cool. So let me stop my share. Yeah. So I hope you enjoyed that. It's a little bit of a challenging problem to get through, but I think that also helps to just solidify what you already know and to clear up some confusions you might have if you were looking at simpler derivations, such as the derivation of the normal Euler-Lagrange equations. Cool. So with the next video, what I'm going to do is I'm going to go into some other tricky things about Euler-Lagrange equations, and that'll be the next video and the video after that.